Welcome to Finite Elements. Today we'll be discussing finite elements. I have invited Marwan Fayed to walk us through the Trusses analysis and how to formulate that in Abacus. I welcome Marwan and thank you for your time.
So today we're going to just go over like a quick overview of what FEM is, the principles, how it works, what it does, why it's useful, why we even bother studying this. And we're going to go into trusses. So we're going to not really focus on springs, instead go for trusses, which is kind of the more advanced subject, and then discuss the direct stiffness method, do a quick example of that, and then we're going to go into abacus and do a truss problem, and hopefully, if time permits, a plate problem with attention. So let's get started. Finite element method. So what is FEM? Just kind of generally, you might have seen this in the lecture, but FEM is essentially a numerical method to approximate solutions of partial differential equations. So it's very widely used in structural analysis. A lot of our work with regards to this is going to be structural analysis, solid mechanics focused. So very useful tool, kind of revolutionized the way we do any sort of experimental analysis because we can just do it on a computer. Saves a lot of labor, saves a lot of material, just a generally very good way to study materials, study loads, study just general mechanics of materials. So basic steps. So we can follow this kind of roadmap right here. So the first step is discretization. That means breaking down the bigger problem into smaller elements. So breaking down a big domain into elements, into nodes, into etc. that are easier to tackle, and we can deal with those on an individual scale. Element equations. So that's just defining equations for each small element, and this typically involves using a stiffness matrix. KE is known. Okay. Assembly is when you assemble all of these elements into one big global stiffness matrix. So taking each individual one and combining it into a global one that just represents the entire big material. So instead of that big plate, it's going to be the small elements, but then we're going to merge it together into a global stiffness matrix to kind of solve our problem. We're going to apply boundary conditions. So this will include applying any conditions that reflect reality, be it supports, be it loads, etc. And then solving this whole entire thing using linear algebra to solve an equation such as the ones we have here, Ku equals F, Mu double dot plus Ku equals F. So it's very rooted in stuff that a lot of you have probably done. MAE 101, statics, MAE 156A. I've probably TA'd. I recognize a few of your names. So some of you should have that background, at least with regards to me, on how to approach these problems. So when it comes to approaching that, it's going to be something similar to what we did in MAE 101, just generally applying boundary conditions, your force equations, functions like that, and then applying the global stiffness matrix and solving for that. So that's generally the hand approach to finite element analysis. But obviously, when you jump into software like Abacus, that's entirely automated. That's just done behind the scenes, and what you see is the result. You see the deformation, you see the loading, the stresses, all that good stuff. Okay? Any questions so far? Awesome. So let's continue. So why do we study springs and trusses? When it comes to springs and trusses, we can think of them as already pretty idealized, discretized elements. So when you think of a truss system like the ones we've dealt with in 101 and 156A, we can deal with the entire truss system. Imagine it looks kind of like this. And this is a truss system, and the nice thing about them is each one of these is already an element, as inherently it's already been broken down into elements joined between by joints, and you can imagine these joints are almost like the nodes. So taking something as springs and trusses already discretizes the structure. So that just completely eliminates this step right here. And when it comes to our element equations for how our stiffness matrix looks, how our F equals Ku laws, they're pretty straightforward for beams under axial forces. So straight beams, vertical beams, even diagonal beams, if they're at simple angles, it's pretty easy for us to kind of set up something like this. So when it comes to springs and trusses, the elements are very clearly discrete, so it's pretty intuitive to work with them. The stiffness matrix is very easy to visualize and understand, and F equals Ku is pretty straightforward to comprehend. So trusses and springs are a very good introductory step before a much more complex system is tackled. Does that make sense to everybody? Awesome. So let's keep going. So when it comes to trusses elements, we've obviously covered this week with the professor. So just a quick refresher, we obviously break down our truss system into elements. These elements join nodes. based on the degrees of freedom, we can have different node numbers. We number these nodes based on the degrees of freedom of each individual one, and that is tied to how the part can move. So naturally, we look at here a roller. That's obviously going to be restricted up and down, but left and right, it's free to move. This pin support, it can't move this way, it can't move that way. It's restricted in these two dimensions. So if we're going to number the nodes, you can imagine them as 0. This joint is free to move up, it's free to move to the right, etc. So we could just ignore that completely. And every single truss element is, or truss beam is an element. So when we take that, we number the elements, we number the degree of freedoms, we associate elements with degrees of freedom, and then we just assemble individual matrices and then assemble a global stiffness matrix based off of that. So today, at least, that's what we're going to kind of be working on. So we're going to start off with a very simple system, and then together we're going to number our degrees of freedom, number our elements, and build our way up to the whole stiffness matrix. Okay, so let's start off with doing that. So we have this system right here, very simple truss, where we have these elements. We have a diagonal element, some vertical, some horizontal. We have a pin, and we have a roller support. So what I want you to do is to start off with numbering the degrees of freedom that we have in the system, numbering the elements, and then together we're going to start piecing together the stiffness matrices when we have some loading. So let's take a couple minutes to try to do that. Obviously, your numbers based on how you number the elements might be a little different from what I end up getting, but as long as the logic is the same, it's totally fine. So let's take a couple minutes and then start working on that together. All right, so let's start with numbering our elements, right? So we're going to go with just a simple, this is 1. We're going to call this number 2, 3, 4, 5, right? So we numbered all our elements respectively. Now, based on the degrees of freedom of each element, or of each joint, sorry, that'll determine our nodes and our degrees of freedom, generally speaking. So obviously at the pin, we can't move in this direction. So I'll just write this down as 0. Can't move in that direction. You can't move in this direction either. You can even omit it. So I'll just write them as 0, but generally if you're writing something like this, you would just omit it. But obviously the pin, we can't translate it up or down. We can't translate it left or right. So there's that. You can only kind of rotate. So obviously there's going to be no reaction moment or no couple, but we can't translate it. This joint right here, naturally it can move up. So, and can move to the right. I'll call this 1, call this 2. Same exact thing with this joint. It can move to the right. It can move up as well, right? Now, with the roller, what degree of freedom do you think it can follow, and which one is it restricted in? Anybody?
Restricted in X, unrestricted in Y.
Yep. So in Y, we have a degree of freedom. We can call it 5, right? And then in X, it can't move this way. So I'll just call this 0, right? It can't move left or up or down. Technically speaking, obviously, like a roller or a set of wheels, you could just pick up off the ground. But for the purposes of this problem, we're just going to assume it's restricted in that direction. You can't crush it into the ground. It's going to push up off of that. So it's almost going to act like a slide, if you remember from 101. It's going to basically behave in such a way that it's going to restrict its movement in that direction. So now what we want to formulate is the element code table. So I'll have a much neater version without my handwriting, but we're just going to start setting up this table, right? So we have how many elements? 5, right? So we have 1, 2, 3, 4, and 5. And we're going to assign each one a code based on what it connects to what. Okay? So element 1 right here, it connects degree of freedom of 0, node 0, and node 0 here, node 5, right? That's how we're going to kind of number it. Element 2 this way, it connects 0 in the x, 5 in the y, to 3 in the x, to 4 in the y. Element 3, what do you think it is? 0, 3, 4. Yes, excellent. You can unmute and just shout. That also works even better. So 0 connects 0 in the x to 0 in the y. We're going to start off with this one, let's say. 2, 3 in the x, 4 in the y, right? Next is number 4. So we're going to have 0, or sorry, this is 0 in the x, 0 in the y, and then 1 in the x, 2 in the y, right? And then for element 5, it's going to be connecting 1 to 2, x and y respectively, and then 3 to 4. That makes sense to everybody, what we did?
Does the order matter?
No, because obviously you could kind of order it in whatever way you want, picking one node or the other. So in that way, it wouldn't really matter. As long as you're consistent with it. Good question. Anybody else? Okay. So let's check our answers. We obviously numbered it the exact same way, but honestly, you could have numbered it in whatever way you like. As long as you're internally consistent in your system, it's totally cool. Like you could have just as easily done 1, 2 here, 3, 4 there. Could have called this 4, you could have called this 5. That doesn't really matter as long as when you're writing everything out, you're consistent within itself. That's totally going to be okay. The numbers obviously are just kind of placeholders in this case. And then our codes are going to look like so, and that is exactly what we were looking for, right? So now we're going to apply external loading to our problem. So this system is now going to have 2 point loads here, 2 P's, one at this joint and one at this joint, just external loads out to the right, right? So now we're going to pull out statics. So we're going to go back to equations of motion, trying to solve for our unknowns. Our ultimate objective with this is to identify our unknowns. So in this problem, how many unknowns are we going to have, or at least kind of reaction forces? Anybody? 3, right? So we're going to have R1, we're going to have R2, and then as you guys remember, the pin is the one with 2 reaction forces, right? So I'll just call this R3, right? However, if you pay attention here, you'll see that all of our external forces are in the x direction, right? So the system doesn't actually want to exert a higher reaction force than it needs to. So if all the forces are in the x, all of our reaction forces are also going to be restricted in the x direction. It's not going to work more than it needs to. It's just going to do exactly what it needs to restrict external motion. So in this case, we can pretty obviously see that there's not going to be an R3, right? That R3 is not going to be resisting anything external. There's not really a moment that it's going to need to resist, and it's kind of clear that R1 and R2 are just going to be equal to P. So we don't even need to worry about R3. They're just going to remove it and make our solution easier or a little more clear, okay? So now we have these two unknowns. How many equations of motions do we need for two unknowns? 2, right? So the first one will just sum up the forces in x equals 0, and it's going to be R1 plus R2 minus 2p equals 0, right? Now that's not quite enough because we have two unknowns right here. Although obviously with the eye test we could pretty easily solve this problem, but we're going to go through it kind of systematically so you understand the process. So we're going to take a moment equilibrium at joint 1. We're going to take the summation of moment around joint 1 equals 0. So it's going to be, assuming all of these beams are of length L respectively, let's just assume that. So the moment from the bottom force obviously is going to be 0 because it's exerted at the point itself. So it's going to be 1 times 0. And remember, obviously for moment we have counterclockwise is positive, plus R2 times L plus P times L. And it's only going to be 1 P because the other P, its line of action goes through the point, the joint itself. So we don't need to worry about it. It's not going to exert a moment. And turn something by pulling on it directly. You got to pull at an angle or some perpendicular distance. So it's only 1 P that's going to create moment. So looking at the system, we can pretty obviously see that R1 is going to be equal to R2 equals minus, right? That makes sense? Okay. So with that said, we can confirm our answers. Yep, exactly what we talked about. R1 is equal to R2 equals minus P, so we're good over there. Now we need to continue with solving the rest of the problem, which is finding the forces inside each individual member. That's what we were ultimately kind of looking for. The force in member 1, 2, 3, 4, 5 respectively, okay? So with the knowledge that R1 and R2 is equal to minus P, let's start going through each individual truss member and finding its reaction force. So obviously for trusses, we have the method of joints and method of sections. Both work exactly the same. And they work because trusses are two-force members. So a truss is a two-force member because all of the forces are acting at the joint. So it's able to kind of resist that. But whenever you have a force acting at a midpoint of a member, it's no longer a truss. They're not going to be two-force members anymore. At that point, it's going to be a frame. So you're not going to be able to use the joint method anymore. You're going to have to use the method of sections and treat them as non-two-force members anymore, as you remember from 101. But for this problem, obviously, they are two-force members, so we can break them down into joints. So if we're going to number the joints, let's say joint 1, 2, 3, 4. So at joint 1, or we can start off with joint 4. So at joint 4, we have force, or at the, let's start off with x, sorry. So we're going to sum up the forces in the x. Our only two forces in x are minus F4 plus P. And then in summation of forces in y equals F5. And that's our only force. So obviously F5 is going to be 0 and F4 is going to be equal to, okay? Now we're going to repeat this for joint 2 and so on. So we're basically going to go through every single part of this truss. So joint 2, we have F2 minus P equals 0. F2 equals P. We have F1 is equal to 0. So only force in Y. Joint 1, we can sum up the forces in X as F4 P plus F3 45, obviously, because it's an isosceles triangle. That's equal to 0. And then we can do the summation of forces in Y, F1 plus sine 45, F3. Okay? So I'll just go ahead to the neater version of this so we can just kind of have a look at them. So we have joint 4, joint 1, 2, 3, 4. The completed kind of equations for all of them. So we have essentially what we need to figure out what every single unknown is. Every single force in each member, we can find out that way. Obviously, in a truss system, we have two force members, and because we assume that the forces point out of the member, that means we're assuming them to be in tension, and that means if it's a negative value, it's actually going to be under compression. So we can just kind of assume everything's under tension until it's negative, then we know it's compressive. That makes sense, everybody? So does anyone not know how to get to this point given a truss system? Okay. So that's for a static problem. And now, if you remember from strength of materials, once you found the forces in each individual member, sorry, someone asked a question. Yeah, we can do that. So they asked if we can upload the slides prior to the discussion. Yeah, we do. I'll do that. Yeah, so now that you found the force in each individual member, you can obviously just divide by the area to find the stress. So a very easy way for us to do that. Now, that was a very simple statics problem. In reality, what we're doing with FEA is a little more kind of tricky and complex than that. We're going to use the direct stiffness method. So to obtain the displacement value. So what it is that basically we're going to take elements, at least in a truss system, which join two nodes, okay? So we're gonna have node 1, we can call I, and node 2, J. And node I and J have 2 degrees of freedom in X and Y respectively, right? So essentially we're just taking a Hooke's law equation where we multiply the stiffness by the displacement to get the amount of force present. So we break it down as node I in the X direction, node I in the Y direction, node J in the X direction, node J in the Y direction. Obviously, whatever you do in node 2 negatively affects node 1. Whatever you do in node 1 positively affects node 1 and vice versa. Displacements, you can displace node 1s based on their degree of freedom. You can move the nodes in the X direction, in the Y direction, in the X direction, in the Y direction, right? So depending on the number of nodes you have, depending on the number of degrees of freedom you have, this will influence your problem. So however, for something like this, it's obviously going to be 4 degrees of freedom with a 4x4 stiffness matrix and kind of build it up based off of that. Does that make sense to everybody? Great. So also moving forward, we can, just as a reminder from the slides, obviously this is just a supplementary material to what has been done with regard to direct stiffness. So I would recommend, if you haven't already, going through Professor Goyle's slides. They're super awesome. Obviously, he recorded the slides as well this week. Check those out too. Just try to follow as much as you can in this class because aside from obviously like it being a class you need to graduate and do well in, it's a very useful skill to have as an engineer. So I took this class as an undergrad and I didn't really pay as much attention as I probably should have, and I really wish I did. So if I were you, I would really try to make the most of this. Professor Goyle is also a really good professor, so try to ask him questions. He's super cool. Just try to make the most of this because it is a very useful skill and it'll really help you in other classes and in your career moving forward, hopefully. So with that said, let's start applying the direct stiffness method to our system. So it's the same system we had right here. So as we remember, the stiffness is going to be EA over L multiplied by whatever we have in the problem. So let's go over one of the rows or one of the kind of matrices to kind of discuss where everything comes from. Okay. So obviously separating K1 from K5, let's just start with K1. This is going to be for member one, right? So this member right here, we will go row by row. So this row, so we have two nodes. We have this one and we have this one. Or you can call it U1, U2. So I'll call this U and I'll call this V. So U1 is obviously U's displacement each direction. So we go as follows. We go U in the first degree of freedom, U second degree of freedom, V in the first degree of freedom, V in the second degree of freedom, and so on. And then this other column is how a force is generated in that based on a unit displacement in U1, U2. So it's going to be, if we apply a displacement in U1, does that generate a force in U1? If we U2, if we V1, if we V2, and so on and so forth. So let's start thinking about this. So we have element one, we have the pin, and that's going to be our U1. No matter what we apply, no matter what displacement we have a boundary condition that the pin can't move, right? So it's going to be zero across. There's no degrees of freedom, as we've kind of established earlier. The pin can't move left or right. It can't move up or down. So all across the board is just going to be zero, right? Now looking at U based on two can move, right? So what we're going to have across here is that U can be affected by displacements in this other one, which can move in this direction, right? So in the Y direction, this roller is unrestricted. So as a result, this term right here, K21, essentially tells us that there's going to be a force in V1 due to U1. Sorry, I'm so sorry, guys. So this is actually V1. Sorry. So this is actually V1, this is U2, this is V2. Yeah, I'm sorry, guys. So now when it comes to V1, that's going to be this degree of freedom for the roller, which is unrestricted there. And based on the displacement in the other one, we can get one. So in its own, we will get one. And if the other one moves, obviously we're going to get a reaction in that one, so we're going to negative term here, right? U2 in that two direction, it's still unrestricted, so it's zero all across, and then V2, we're going to get that one. That makes sense to everybody?
Sorry, do you mind just re-explaining that?
Yeah. So basically what each row represents, so if we think about the rows in each individual matrix, or in each matrix, it's the relation between the force and the displacement. So in row one, where we have it as an unrestricted kind of, where we have it restricted basically, so the pin support can't move across, there's not going to be any force and there's not going to be any displacement, right? So our stiffness matrix is going to be zero there. The second one, our roller is unrestricted in that dimension. So what we're going to get is that it can move in that direction, essentially. Let's do 2 and 4. That one might be a little easier to somewhat convey. So if we think about the forces here at K2, so the member 2 connects this one with this one, right? So a displacement in this one causes a force in this one on a one-to-one scale. A positive displacement leads to a positive force, right? So we get a positive one here. Because it's a horizontal. What's up?
There's no, you have class here. Is there?
Sorry? What is?
Sorry. I will ask the department. Thank you so much.
I thought it was talking to me. So with that, so this one, when we're looking at this node, in the one direction, it's obviously a horizontal node, sorry, or member. So in the one direction, left and right, a displacement in that direction leads to a force in that direction. So we get a one-to-one influence there. In the two direction, whatever displacement we apply in that direction, in the perpendicular direction, that's not going to cause any stiffness in that horizontal direction. Sorry. So if I move it this way, if I move it that way, that's not going to really influence me in this direction. It's not going to cause any stiffness for me there. My stiffness in the member, because it's a straight truss, is going to be any displacement left or right, up or down in each one. If you imagine it as crushing the truss or stretching it, what that affects in terms of force. So moving this truss up or down, that's not going to cause it to really crush or expand. So as a result, we're not going to get any correlation in the two direction here. Now, if the other node perpendicular to this moves in the positive direction, this one will have to exert an equal and opposite force to restrict that motion. So we get a -1 right here. Okay, does that make sense? So then zero, anything in the two direction, like we've mentioned in the perpendicular direction, that's not really going to affect us or generate a force because it is a horizontal member. And then looking at that third row, at -1 comes from, obviously, if we move this one now, the other one is going to exert an equal and opposite reaction. So we get a -1 right there. And then for the two, the second joint right here, that second node, if we move it to the right, it's going to generate a positive force to the right, and so on. Does that make sense, everybody?
So basically, what this is trying to say is, sorry, Jonas raised his hand, but I talked over that. But basically, K1 and K5 basically has allowable motion in the V1 and V2 directions, while K2 and K4 have permissible directions in the U1 and U2.
Yeah, exactly.
Okay.
So there's even another. So if we look at this, based on our, sorry, do you have a remaining part of your question?
No, that.
So yeah, the good question, Jonas. They are symmetric because we really only need to generate this part right here. Obviously, this is the diagonal part, but this part is just going to be mirrored because it's going to be equal and opposite reaction. So whatever you apply on that direction, the other one is going to be equal and opposite. So it'll just get flipped to the other side. So with that, now that we've generated these local stiffness matrices for each of the members, now we can start generating our global one. So what we do is we take each individual local stiffness matrix, we write our code across the row, across the column, across the row, across the column for each individual one, right? So obviously, member one, we had the code 05. So we're going to do that across the columns, across the rows, up and down. Same thing for each individual one. And we're going to take that into our global stiffness matrix. And we're going to do it term by term, basically. So it's going to be pretty menial when we do it, but finite element analysis as a software will make it much easier. But it's also pretty important for us to know the theory. So let's go through it together. So our first term in this global stiffness matrix is going to be that one term right here. So what we're going to do is we're going to look across all of our matrices and see if a 1 shows up. And where does it show up? So we look here, there's a 1 here. We see right here, across this one, there's a 0 right here. Look at the others, 1, there's a 1 right here, across this one, right? We're going to add these two. We just sum them up, and the sum of them is obviously going to be 1. We put a 1 right here. That's our first term. Now we go to the next term. We have 2, 1. So we look across. Where's the 2, 1? There's a 2, 1 right here. We went here. There's a 0. We look for a 2, 1. There's a 2, 1 right here. 2 here, 1 here, another 0 plus 0. It's going to stay 0. We just end up right here, right? Then you go through each one. So that's basically the hand process. It's easy. It's just going to take some time. The next one, 3, 1, we can go here, 0. The next one, 3, 1, it's just 1, I think. So it's just a 0. So we'll put it right here. But you're just going to basically go all across. And actually, because it is symmetric, you can go through the diagonals. You can go through that top right and then just mirror it. So that'll make your work a little bit more. Go ahead with all of it. But once we have this, that's basically all of our work. And once we have this stiffness matrix, we can now get the displacement. So ultimately, finite element analysis, what we do is we prescribe external loading, we prescribe boundary conditions, and we want to figure out how every single part of this structure moves. So we have assigned material properties, we've assigned dimensions, we've assigned some CAD model to represent our structure. We've represented boundary conditions in our own stiffness matrices that are reflective of our kin, of our roller, etc., and our external loading. So we take this stiffness matrix and we just basically say that, hey, Ku, the stiffness matrix times the force, or times the displacement equals the force, and that force is going to be equal to the external force. So we can move this to the other side and say that the displacement on its own is just equal to K inverse F, just a simple matrix multiplication to determine what our displacement is. And that's basically our ultimate goal. So as an input, we've assigned all of the things I've mentioned. As an output, it's the displacement. So ultimately, what we visualize in FEA is how much each of these nodes have moved. So it's going to say, hey, In the one direction, this is moved this. In the two direction, this is moved this way. And this is done on a node by node basis across the entire structure. So for a truss like this, it's something very simple for us to do. But imagine it's a part with thousands of different elements, with thousands of nodes. It's a very complicated process, but this is exactly what happens there. Obviously, for different elements, it's somewhat different, but here it's a simple element with two nodes attached to it. Obviously, in FEA, you can have triangular elements, you can have quadrilateral elements. Those are obviously more complex, but as a very ground level principle, this is what's going on. You're generating a stiffness matrix, you're generating external loading, and you're mixing those two together to computationally determine the displacement. So as the theoretical side of this is what's going on. So do you have any questions about that? Now, the next step would be actually applying that. So this class is obviously two halves. One half is understanding the theory behind this, and the other half is actually applying that in Abacus. So any questions? Awesome. So let's do, instead of 10 minutes of a break, let's do 5 minutes, and then we could just finish a little earlier. How does that sound? Anyone object to that? Okay. So let's take 5 minutes. Does everyone see my Abacus? Yes, no?
Yeah.
Okay, perfect. So this is Abacus CAE. Well, assuming 90% of you guys will be using it through the VDI, like the virtual desktop interface. If you download it locally, that's probably also fine, even better, honestly. My version is 2017. For the demos, I don't think it should really matter. If anything does come up where I'll have to be on the version you guys are on, like the newer one, I'll adjust it, but they don't really iterate too much between versions of Abacus, so you'll probably fine, to be honest, between them. It's kind of like FIFA. They don't really change much between them. But let's get started. So what I did when I first opened Abacus was selected standard explicit. So that's kind of the directory I use, the standard explicit model. If you're following along, that's pretty much all I did. So I just click that, and then we end up at this blue screen right here. So what I'm going to do is I'm going to open the part tab. So as you can see, you have a bunch of different tabs. These are basically almost one-to-one the process we're going to use. We're going to create a part, apply properties, assemble it, create our step, apply the interactions, loads, mesh it. If we need optimization, we do that, then run our job, and then we can visualize the results based on that. So pretty handy. This is essentially step by step what we're going to be doing. Actually, let's go back to the slide so we can describe the problem we're about to do. So it's a very simple problem, very common problem, right, straight from a textbook. It's a truss problem. So we have the following truss system where we have a fixed support right here, or a pin, sorry. We have, or I think this is fixed actually. Imagine this is fixed. Roller on the right, we have 2 point loads, 1,000 newtons down. The length of each member we're going to assume is just 50 meters. The cross-sectional area is 1 square meter. The Young's modulus of the material we're just going to take it as a steel of 200 gigapascal modulus and a Poisson's ratio of 0.3. Jimmy, we in the first half of this we covered like the theory, so we just did a quick revision on trusses, what FEA is, how to assemble a global stiffness matrix, and then now the second half of the discussion we're gonna do, just like an Abacus demo, we're gonna do two problems, one truss one and then a plate problem. Okay, so yeah, so here's the problem. Basically, you could take a screenshot, write it down, but follow along essentially from here. Now, what we're gonna do is first create a part. So we're gonna go into part. We're gonna create a new part. Okay. This tab will pop up on the other one. So it's gonna be 2D planar. I'll just call this truss formable. Sure. I'm gonna assign wire features. So it should start off a shell, but you want to switch to wire if you're gonna do a truss problem. Okay. So 2D deformable wires. Okay. Create new part. And now we have the design or the part creator section. So if you've used any other kind of CAD software, you should be pretty good with this. If you've used SolidWorks, etc., I think other softwares have something similar, but it's not too complicated. So we're going to use this one at least for lines. So it's a little different from SolidWorks. It's not as intuitive as that. You're going to go here, and we're going to start creating lines to represent our truss system. So we're going to go like this, like this. We're going to go like this, and then one more line across like this. Okay. So now we have the general kind of skeleton of our truss system. What we're going to do is we can prescribe dimensions. So using this one right here, I can prescribe some length to my truss system or different elements. And I can also prescribe constraints. So I click this, I'm going to get the constraint tab. We can do a horizontal one on these, obviously, because they're going to be straight. And then this one right here, okay. These two horizontal, okay. Oops, sorry, go back into the part. Okay, here. Yeah. So horizontal, this one. All right, yeah. So now we can prescribe lengths. So we could do and then this one. If I define this one, it'll become over defined, as you can see right here. So it'll turn pink. But I could just undo that, and then it's going to be adequately defined. Okay. If you just put too many constraints, it's yeah. Jonas, you have a question?
Yeah. Sorry, I think maybe a few of us were still setting up Abacus. Would it be possible to quickly reiterate what the steps were to create the truss?
Yeah, yeah. Let me just delete the whole thing. So I'll just create a new model, standard explicit, save changes, no. Okay, everybody, good to start now. Okay, let's go. So we're gonna hit part, create new part, 2D planar, deformable wire. So we're gonna look for wires features to create trusses. So we're gonna continue. We're gonna go in here. We're gonna model the trusses kind of general shape. So, oh, sorry, I forgot one element. Like this. So we're good here. Right. Start modifying stuff. Okay. So we're gonna change the dimensions. So we click this to adjust dimensions of each individual part. So 50, we said each element is going to go 50 here, and then we now have an adequately defined system. Okay, right. If you want to re-access your part, you just look on the left here, model one part. So find your truss, wire, and then you just double click your section sketch, and then you can paint whatever you want. Okay. Any further edits from this point will over-define your sketch. If you remember from SolidWorks, that can happen where if you prescribe too many dimensions, too many constraints, that could mess with your setup because it's like, this is just too much information. Or if it's like something very obvious that you're assigning, it doesn't like that. So you just need to do enough to define your problem, but past that point, everything's okay. Because if I go here and prescribe a 50, it's going to turn pink. So it's just an over-defined sketch. So at this point now we're done. And now we have the first part of this done. The part itself has been created. Now we're going to go into our property tab. So we're going to property and we're going to create our material. So we're going to go into create material. This tab will show up. We're just going to create a steel. We're going to go into mechanical, elasticity, and elastic material. So that's just one where it's going to be linear elastic. All we need is a Young's modulus and a Poisson's ratio. So we said that the modulus is 200 gigapascal, so 200 E9, and then our Poisson's ratio is 0.3, and that's really all we need at that point. So we can hit OK past this point. Any questions on this so far? Anyone? So at this point now we've defined our material. We now need to create a section. So I'm going to create a section here. I'll call it a truss or call it our truss. And we're going to assign it to be our truss section. And then obviously here at the beam section, you'll find it to be a truss. So you're obviously going to click that one. Okay, you probably start off in solid. So just click beam and then click truss and then hit continue. And then the material we're going to assign to this section is the steel. And our cross-sectional area is 1 as our problem kind of specified. Okay, that makes sense? So once we do that, we hit OK. So now we can assign this section. So we hit assign section. We select this entire region, done, and we assign it the truss section. Okay. So we're basically saying that, hey, this part is this section, and this section has a material system attached. So this is useful when you have different material properties for different sections and so on. This is why we need to do that. We need to tell it, hey, this is this section, and this section follows this material law. So once we do that, we hit OK, and the color is going to change, essentially saying, hey, you now have a material assigned to this truss. Okay. So any questions so far? So now we go into the assembly tab, and it's here that we're going to create an instance and actually bring our part into this. So we create instance, we bring the truss, and then we just can hit OK. So we brought our part into this. Now we can start creating the actual simulation itself. So we go into step. Any questions so far? Is everyone following? Okay. So we can create a step, and it's going to be a static general step. So just step 1, an initial step, a static general step. Continue. Don't worry about this for now, but you could create smaller increments. If you want to get more steps, you could play with a nonlinear geometry. But for this, it's a very simple problem. Just hit Okay, so we've created our step. We've created everything else. Now we need to prescribe our loads. So any boundary conditions we have for external loads, this is where we do it. Tab right here. So let's start off with the boundary conditions themselves. So we're going to create the fixed boundary condition here. So we're going to click this. Here we go to the initial step and we're going to say fixed end right here. And we're going to prescribe it a symmetry. Okay. So we click continue and we click the point at this corner right here. That's where we're going to have that boundary condition. This tab is going to show up and we want to restrict it in all degrees of freedom. So U1 equals U2 equals U3 equals R1, R2, R3 equals 0. So it's just completely fixed. Jonas, you have a question?
Yeah, sorry. You can ignore this if everyone else is able to keep up, but I feel like I've gotten really lost in the sauce from like setting up everything and then like I believe you cannot do the following steps if you missed one of the previous steps.
Yeah. In that case, just I'll upload the recording tonight, so you can just like watch it back if you want. Like, I would honestly just focus on following what's going on, understanding why we're doing what we're doing, and then you can just apply it yourself whenever you want.
All right.
Is that cool? Who else raised their hand? Lucas?
In this specific example, since it's like a 2D system, would it just not be sufficient just to set the X and Y displacements to 0?
Yeah, it would. It's a 2D problem, so yeah, it's kind of like obvious, but yeah, U3 wouldn't really matter. The 3 wouldn't really matter in this case.
Gotcha.
Yeah, if it's a 3D problem, that's when that would come into play, but yeah, in this case, it wouldn't really matter.
Okay, thank you.
Of course. Any other questions, guys? So once we've assigned that, this end is now fixed, and you can see right here, we see some demonstration that there's a boundary. Yeah, Jonas, you got a question? Okay. You raised your hand, so I thought you had a question. We're good? Okay, that's just good then. So now we're going to do the roller support. So same exact thing. We go here to create boundary condition. This one is going to be the roller, obviously. We're going to go to step 1, and then we're going to create the other boundary condition, and then we prescribe a displacement rotation boundary condition here. Continue. We're going to click this right end here, hit done to accept. Now we can edit the boundary condition, and this is when you could do it manually based on what you need. So if we have some custom roller or some specific design that we need, we can prescribe what we need for it. But obviously a roller, we want to restrict it in the 2 direction, which is the Y direction. So I'm just going to set that U equals 0. Does that make sense to everybody? And I'm just going to hit continue. Okay. Now we see the roller support is right there. Now, with that said, we start doing our forces. So we're going to click this tab right here, create load. This tab will show up. I'm going to do a concentrated force, obviously. Load 1, we'll just call it that. I'm going to click this point here at the bottom. This is where that load is applied. Done. I can edit the load to prescribe what the force is. So I'm going to do it in the 2 direction. It's going to be a force of, I think, minus 1,000. Okay. So this is going to be a concentrated force just pointing down, or a point load. Okay. And then we hit OK. Then we do the same thing for the other force. So create point load, concentrated force, same exact process. Continue. And we're going to do it at this end right here, the force point. So load 2, point here, hit done. And then the same direction, the Y direction, but this one is also minus 1,000. So then we hit OK. So now we have our forces. We have this 1,000 force down, we have the roller support, and we have the fixed support right there. Does this make sense to everybody?
I have one more question on the setup of the boundary conditions. For the fixed support, we set the step to initial, but for the roller, we set it to step 1.
Yep.
Why did we choose a different step for each of them?
So some boundary conditions you have to kind of set up differently depending on the nature of them. So the fixed support, because it's something inherent to the actual like setup of the problem, you have to prescribe it in the initialization step. So because it's restricted in all degrees of freedom across. But the other one is that when the problem starts setting up, it can't move. So it's basically saying that, hey, in the initialization of the problem, this roller could move. But once the problem starts and we actually start accounting for the loads, the roller can't move. It's just a different kind of nature of the boundary condition. Does that make sense?
Yeah, thank you.
All right, any questions, guys? Cool. So let's continue. So now that the loads are done, we can continue to meshing our part. So we're going to go into mesh right here. And we're going to hit the part itself to bring the part as a whole. Now we need to do a special type of mesh to essentially make it behave as a truss. So the first thing we need to do is seed our part. So we hit this thing right here, C part, this tab will pop up, approximate size. So because we wanted to have one part or one element per mesh or per truss member, sorry, we're gonna assign the size to be 5. So that way it'll end up being one member or one element per member. 50, sorry, because the lengths are 50. And then everything else is totally fine. We hit apply to this. We've now seeded our part. Now we need to change one small thing. We need to change the type of element. So feature mesh element type. We select that part itself, hit done. Now this tab will show up with different families of different types of elements, basically. So we go here, we go to truss, and we can assign the type of element we have to be truss elements so that they behave in two node linear 2D trusses where they can either compress or be tensile. They can't really do much else aside from that. Okay? Force members. Okay? Does that make sense, everybody? Cool. So we hit OK. Once we have this, we could select everything and then we mesh our part. So we click that. Okay. So we click yes, mesh the part. Okay. And now our part has been meshed. Any questions now? So with that, the problem is basically ready to be solved. So we go to job. We can create a new job. So I'll just call this job 1 for model 1. This tab will pop up. Based on your computer, you could feed or use multiple processors. So like 6 for this one. But 2 is fine, especially for a simple problem like this. You would be totally fine. And then you just hit OK. And then we can submit this job. And it's going to pop up here in the job manager and hit submit. And the job will start to run. The job already exists. Okay, override. Yeah, I think I already have a job file here. And we can monitor this as it's running. So it's submitted. We can monitor it. It's been submitted. And we can just kind of track the steps. If it's going to fail, you'll see that happen live. But you'll basically be able to track the job as it goes along for each increment, for each step, and see maybe where it went wrong, how many iterations it took, how many attempts it took, so you can get an understanding. Okay, I think it's complete. We can hit now results. So now this is our undeformed part. Now we can click this and see our deformed part. So this is our deformed truss. Okay. Now I just want us to be able to get to this point and for us to feed loads to feed like boundary conditions, to feed material properties, and for us to be able to get some output of deformation outside. So that's basically what we did today by hand in the FEA kind of hand calculations. This is the output. This tells us at what node displaces by how much. And this is obviously undeformed. This has not moved. This was a restricted one. This was a restricted one. These went down. This went down. But that's basically what we're looking for. If you pay attention to here, you'll see a deformation scale factor of 1.412 times 10 to the power of 7. So in reality, this truss didn't really deform that much. It assigned a much larger deformation scale factor, actually visualized the problem. That's why the deformation is so dramatic. But in reality, it actually looks like this. So we can press this button right here, common options. We can do auto compute. It's auto computed to be 1.4 times 10 to the power of 7, but we can just do a uniform one of 1. And this is actually how much it's deformed. So you can obviously see it's not deformed at all. The force was just too little and the material steel was too stiff for us to really get a deformation. That's why you have to increase the deformation scale factor to really see some discernible deformation. But we can now see the von Mises stress. We can check S11. We can check the stresses in each direction. We can check the deformation, the U magnitude. You can probe different values. You can check at U1, at U2. But for now, at least, this is kind of what we're looking for, is for us to be able to set up a problem, to design a part. Oh, Jim, you had a question?
Yeah, I was just curious, like for this problem, you kind of assigned a predetermined load into the middle of that truss.
Mhm.
But for the homework, they're asking how much load it would take to break the truss, I think.
Yeah.
Is there any like instruction on how we would like solve for the maximum possible load? Or yeah, like I know there was a link provided in the document, but I don't know if that went into how to do that.
Yeah, in the link, there's a tutorial for how to do that.
Okay, sick. Sorry about that.
No, no, you're good. Any other questions? Cool. So let's kind of just run back on what we did and how we did it in case someone maybe kind of lost track at some point. So we went into the parts tab. That's basically our first step in kind of creating our part itself. So we went into the part, we created a new part, we open up this tab. we draw our part manually. So we did it with the lines. We drew this truss right here. We can assign constraints. We can assign dimensions to create our part. So based on, let's say we want it to be fixed, we can prescribe that. We can prescribe it to be coincident, 2 points coincident, some points or some lines perpendicular, horizontal, etc. That's very useful. You can even dimension parts. If you have already assigned a dimension to a part, just click this right here to edit it. You make it longer, shorter, whatever you like. But that was the first step, just creating the part itself. Okay? Okay. Next is the property. So this is the tab where we create materials and assign them to different parts. So I've already created a material in steel, but I went into this tab, I clicked mechanical, elastic, and with an elastic material, the two only quantities you really need to know are the Young's modulus and the Poisson's ratio. Prescribe that, assign it, we're all good there. We create a section which tells us what is where. So we created a section right here, the truss section. We prescribe that that part is in that section. Then we assign the section to a material, and that's the step to essentially say, hey, this part behaves with this material law. We created an instance to bring this part into our simulation. That's in the assembly tab. Next is the step. So we just created one step, a static general step, where we apply the loads at that step. Initialization is just that step right there. So it's it's one step, but you could think of it as two pseudo steps where there's an initialization step, then the actual proper static step. Now, in the interaction module, we didn't need to use that for here. Load, we applied our fixed boundary condition at the left using this. So initially we had a fixed end right here, and this propagated all across. The roller boundary condition, where all we're doing is restricting displacement, we can just create it at step one. We don't need to initialize it over. Okay. And then our loads, we created load one, load two, point loads pointing in the y direction down to be negative. So that's all we did. And then we meshed our part. We used a special mesh for it to behave as a truss. And then we just seeded our part, assigned the special mesh type, and then we just assigned the part. And we made it so that each element was size 50. So it's basically one element per member base. Okay, so it's very easy to deal with. Then at that point, we just created a job. The only special thing I do was just increase the number of processors so it runs a little faster, but it was perfectly fine for this. And then I ran my simulation. So when it comes to this, do we have any questions? That why is global size 50? No, okay, so Ethan, I think I answered that, but if it's not clear, let me know. Said, could we initialize the truss without any boundary conditions and add the fixed roller in the later step? I was just curious why you need to be sued. Yeah, you could. I think you could do it that way. I don't think it would really make a difference. I think though for correctness at least, especially when you do 3D problems where you need all degrees of freedom to be restricted, it's best to use that in caster boundary condition so you can fix it in all directions. Does that make sense, Jimmy? Yep. Any other questions, anybody? We're all good?
I have a
Okay.
question about the homework.
Yeah, of course.
So for the part where we're supposed to do it analytically, like manually without Abacus, are we allowed to use MATLAB or like do you expect entirely like pen and paper calculation?
Yeah, you can use MATLAB like for calculations. Yeah, of course you can use MATLAB.
Okay.
Yeah, I don't see why not. Any other questions? Okay, awesome. So we've done now the first problem. We have one more to do. I think we'll have enough time to do it. It's a little more of a complicated one, or a little more complicated, but it's still quite simple. It's just a simple textbook problem where essentially we're going to take this plate right here. We're going to have a hole in the plate. All these dimensions are in millimeters, obviously. We're going to have it as a built-in support or fixed support on the left end, and we're going to apply a stress of 10 megapascals or a pressure on the right end. Okay? Our Young's modulus is going to be a material of 200 gigapascals, so same material law with a Poisson's ratio of 0.3. But now it's going to be a little bit more of a more complicated problem than the truss. So let's begin. Go back to Abacus. You can save that truss project if you would like. So if you want to do that, you could just save as, and then you could export the CAE file wherever you want. I already have one, so just make a new part. Okay. So new standard explicit model. Save changes. I don't need to do that, and then we're good here. Okay. So same exact process. We start all the way up here at the part, create our part, go through every single step, very similar to the truss, except it's obviously not exactly the same. Okay. So we're going to create a part. It's going to be 2D planar still, deformable, but it's not going to be a wire anymore. We're going to create a shell part. Okay. Size 200, same thing. Okay. So shell now means it's going to be a real part with volume, a real part as a plate, as a deformable material, not a wire anymore, which was just thin kind of truss members. Okay, so continue. I'm just gonna call this plate or whatever. Continue. Okay. So now we're gonna create the geometry. So it's rectangular. So I'm gonna just start off with the dimensions. We said that its length was 100 and so 50 here and 100. Okay. Then this will go all the way across, and then we just need to assign this circle in the middle. So we've done the rectangle. Now I'm gonna make a circle, center circle. You can put it wherever you want. I'm going to create the circle itself. And now through dimensions, we're going to position it right in the center, okay? So we create the circle. I'm going to do a radius of, I think, 10, I believe it is. Yep, R is 10. And then we're going to position it in the center. So I'm going to assign that this distance between this and this is going to be 50. And then the distance between this and this is going to be 25. Okay? And then I think this is sufficiently defined. Let me check the chat. Change units to millimeters. No, so it's not. So great question, Ethan. Abacus isn't quite like SolidWorks where you have a unit system within it. Everything is kind of dimensionless and is prescribed up to you. So if I do this in 50, 100, etc., then I'm going to essentially in the material properties and whatever adjust accordingly such that it is in a SI unit in whatever dimensions you want. Does that make sense? You kind of have to keep track of your units on your own, which is kind of a pitfall people can have where, yeah, if you make your dimensions too big in one length scale and then you don't pay attention, like the loads or something, that could give you some trouble. So just be very careful with that. Yep. So I think we're done here. I don't think we need to do anything else. So here's our part. It's going to be the plate with the hole. So now we go into property and we create our material. So same exact process. So we hit property, we hit create material. We're going to create steel right here, mechanical, elasticity, elastic, and then so 200 gigapascals. By the way, Ethan, you were right in that because the problem in the textbook at least said it's in millimeters, I should have done it in millimeters on Abacus, but because I wrote it in just 50 and 100, it's going to treat it as meters, which is fine for this demonstration, but in if you want to do it correctly, you would write 50 times 10 to the power minus 3, 100 times 10 to the power minus 3, such that it is in millimeters. Okay? Good shot, though. So Poisson's ratio is going to be 0.3. Young's modulus 200 E9. I think we're all good here. We hit OK. Now we create a section. So it's not going to be a B, or it's going to be a solid, obviously, a homogeneous solid, which I'm just going to call the plate section. Continue. And I'm going to assign it to steel material. Is everyone following up until this point, by the way? So steel section, homogeneous, we assign that. I do material steel, okay, we're all good here. Now we need to assign this section. So we hit assign section, we select the part, we hit done, okay, plain section, okay, we're all good here. Now it's gonna turn this teal, I think, color, and that essentially means you have assigned a section and then a part to this section, okay? Now we're all good here. We can then go to assembly, and all we got to do is just create an instance where we bring this part into it. Okay, that's all we got to do. We just hit OK. We now brought our plate into simulation itself. Now we can go to the step tab, create a step, another static general step. I could just call it step 1. That's fine. We don't really have to change anything either. But just keep in mind this nonlinear geometry, if you have very complicated loading, very complicated geometries, you would turn that on such that this software can, or the CAE can actually kind of adjust for that. But for us, it's a very simple problem. We don't need to turn that on. You don't need to worry about that either. This is like for incrementation. So if we want to kind of more finely track our simulation, we could do that. But all we just need to do is just hit OK here. We've created our step. Okay. So any questions so far? Now we're going to go into load and assign our boundary conditions and external loading. So we have the fixed boundary condition and the pressure on the left side. So we're going to start off with the boundary condition here. So I'm going to go into here. I'm just going to write the fixed support, call this that, static, put it all in the initial so that we can do that fixed support boundary condition. And then we're going to do symmetry, anti-symmetry, and caster. At that point, you can select the region as this left end right here. We hit OK, and then we could just select U1, U2, U3, UR1, UR2, UR3 equals 0. Okay, that's going to be all across. So here, and you can see right here that the support has been rendered, and we have that right there. Now we're going to apply a load. So create a load. I'm going to do it in step 1, and I'm just going to call it the pressure. Oops, sorry. And it's going to be naturally a pressure. So we go here, select continue, and we're going to do it on this surface, this right end. Okay, hit done. Tab will pop up, and then we can prescribe the magnitude of it to be minus 10, right? Yep, 10 megapascals. Okay. So yeah, 10. So then you do 1, 2, 3, 4, 5, 6. Okay, 10 megapascal. Okay. Any questions on this? Okay. So now we can mesh our part. So we're going to bring the part in. We click this. So then we hit mesh right here. We want to set an element type on this entire thing. Okay. So I think by default it's plain stress, but there's a bunch of different other stuff, but we could just stick to plain stress. So we're just going to hit OK. We're going to go into mesh controls here. You can have a free mesh right here, which is pretty much the only option we have, but I'll make it a non-symmetric. So I won't partition this part just to demonstrate to you what that's going to look like. When it's a free mesh, it's just going to kind of do the part all across a pretty disorganized way, and the part will look disorganized as a result. That's what that's going to end up doing, but we'll hit continue. But what we're going to do is once we run our simulation, we'll go back, or once we mesh our part, we'll go back, we'll partition it so that it's in 4 parts, mesh each of these 4 independently such that it's structured, and then as a result we'll get a much cleaner looking mesh. Okay, so we can just hit OK here. Any questions so far? Awesome. So let's see the part. So I'm gonna see that to be 10. I think it's fine. Okay, apply. Actually, I think this is fine. Hold on. Actually, I can make it finer. Apply. Okay, yeah, and then I could just mesh this part. Yeah. So as you can see, it does end up being a little disorganized looking, as like so, which we can partition and get a more organized part. But I think for now it's fine. I just wanted to demonstrate that the mesh isn't going to be so structured when you have it be a free mesh. We can do the partition. Let me just do that anyway. We'll go here. We go back to part. We'll go to partition space sketch. So it'll say some meshes will be invalidated by the partition naturally. Yes, okay, that's fine. Delete meshes. Okay. And now we're just gonna draw 4 lines, or 2 lines. So one like this, and then one like this. And I think that's all we really need to do. Done. So now the part is partitioned. As you can see right here, it'll show up on the part itself. Then we go back to the mesh, and I think if you can go into mesh controls, you can now do a structured one. So this structured mesh, that's going to be the far more organized one. For this simulation, either one would have been fine just because it's such a simple one. But moving forward, I think neater meshes just do better, or obviously finer meshes do better. So we're going to hit structured OK, and now just remesh the part. And as you can see, it's a lot smoother, a lot cleaner, and we're just going to get a lot better results from this mesh. Okay, that makes sense to everybody what we did? Instead of a free mesh where it went kind of all the way across and had to deal with this individually, we meshed 4 individual sections separately, symmetric ones, and we got a much cleaner mesh as a result. That cleared everybody? Any questions? Okay, so that was all we really needed to do at that point. We could just create a job. So I'll create a job 1, model 1. Parallelization, kind of up the number of processors so it runs a little faster. Okay, we click this, we can see our jobs submitted, and then we'll get our results in a second. We can monitor it as well. Here, the pressure might be a little high, but we'll find out how it looks after. Okay, so it's done. We click results. So this is going to be our part, and then here it is deformed. So this is a 1 deformation scale factor. But as you can see, we get the deformation. It's a very slight deformation, so I can up it, to be honest. I can be like, let's try 10. It's going to be a little bigger, 100, 1,000, and so on. It's just going to get more and more dramatic, obviously, until it reaches this point. But the pressure we applied was very low, so it didn't deform the part that much. But what we do see is we see deformation, we see stress distribution. So obviously around the hole, there's going to be stress concentrations. We can visualize that here. We probe it, can figure out what we want from it. We can check. So S is going to be our stresses, so we can check S11, kind of plot it all across at different points, S22, That's in the y direction. S3, obviously, no 3 direction at this point because it's a flat plate. Next principle, on VC stress, so on and so forth. You're familiar with that. Now we can check our displacements. Obviously, at this end, very minimal displacement, maximum displacement going to be here. All very low quantities. All of our displacement going to be in the one direction. Really nothing or something very low direction. Right. So, Jimmy, you have a question?
Yeah, in terms of units, so when you dimension the lengths, those were in millimeters, right?
No, I messed that up. So I put it as just a straight, like we can go back to our part. So here, shell planar. I did it as a reality, it should have been 100 times 10 minus 3.
Right. But didn't it almost work out because you put your pressure in like 10 megapascals, so like millimeters and megapascals almost like canceled out if you like just
No,
split them
I
as
did it all the way. So I did pascals.
okay.
I did
Okay.
10 with 6 zeros behind it.
Roger. Okay. So the value numerical values and the stresses are not meaningful to us, I guess.
But this is just a demo, but yeah.
Okay.
Yep. It's yeah, if you do want like a practical value, you would change this to be millimeters. And then at that point you would see a far more dramatic kind of deformation. So you go back to visualization, obviously here. So realistically, like we can even play around with the deformation scale factor to get something more realistic. So if we're missing this is how it would have looked, a bigger kind of deformation right there, right? But the deformation scale factor of 1, that's how our problem really was. Ethan, inch, pound, second, that would be, like I said, everything is kind of defined by you in your own kind of definition. So if you want to do inch, pound, seconds, you assign whatever lengths you want. Your forces, you assign them based on your own calculations, material properties based on your own calculations, etc. It's done independently on your end. Everything is dimensionless in the abacus. It's really up to you to do the math on your own end. That makes sense? It's not like SolidWorks is where, yeah, like, like SolidWorks is going to have you assign a dimension like inch, pound, second, SI, meters squared.